this is a little different than some of the webinars we've had. I want to talk about some advanced tips, things you can do to improve your system for very low cost or free. These are this is kind of these tips are these are what the guys know that do wireless for the Olympics and for the Enormodome and for the Super Bowl. These are what these guys do, although they do it with a lot of measurement, a lot of calculations and that. But I think you can see you'll get sort of the rule of thumb for these things, and you can look and see if any of these are negatively affecting your system. So we'll kind of buzz through them with that in mind. The first one you probably know, but maybe not everybody's aware, or everybody's aware of the same. And that's you don't want to let the performers block your line of sight. Typically, what I see a lot of are people holding microphones, wireless microphones from the bottom, and that's where the antenna is. Radio waves don't like to go through water, and so your water bag hand blocking the antenna is an easy way to lose 20 dB of signal. So I would coach all your performers to please hold the microphone in the middle. Actually, I was thinking about maybe inventing a barbed wire cap to slip over the bottom there, but so far nobody's thought that was a good idea except me. So you want to make sure that they're not blocking that antenna, because that's a tremendous amount of signal to lose, 20 dB, by doing that. And it's even worse with belt packs. So this is a pack that's used for performers in plays, and a lot of times, or TV, sometimes these folks don't have any other option. They have the things have to be hidden under costumes and that. But if that antenna comes in contact with your skin, or that antenna is only the thickness of a piece of cloth away from your skin, like putting your guitar transmitter in your pocket, or your belt pack transmitter in your pocket instead of putting it on your belt, you could lose 40 dB of signal if it's on a big person. And literally just moving that antenna half an inch away from your skin can bring that back to almost nothing. So that's something you want to watch. It doesn't happen all the time. Again, unless you're doing Broadway plays, and sometimes you have no choice. Or for TV personalities and stuff, they're very particular about sight lines and that kind of thing. But usually those folks are only working at 10 or 20 feet, so they have that advantage. But if you have to work with somebody, the normal 20, 30, 40, 60, 80 feet away from them, you want to watch and make sure that you're not covering those antennas, you're not touching those antennas. It actually detunes them as well. So whatever frequency you think you have, if your antenna touches your skin, it shifts it a little bit, which means it's not perfectly lining up with your receiver, which, it'll work to a point and then it won't. So this is something you want to watch for. Real easy one. Okay, the second one, this probably makes no sense to most people. What crazy thing is he talking about? Make your antennas weaker. Well, you don't really make your antenna weak, but what we're doing is we're going to block some of the signal that comes from that antenna before it gets into the receiver. And the way you do it, you use these BNC inline attenuators. This is a page I cut out of Amazon. These things I've seen them from $10. I've seen them for $40. Pretty much it's just a pair of resistors inside that body. So I think what you're getting if you buy a more expensive one is maybe a more robust mechanical body than a lesser one. But, that's up to you. They're very easy to come by. You can get them from any kind of parts store that sells, coax and connectors and that kind of thing. But you can get them on Amazon. So you can have them tomorrow if you want. And there's all different, you just need to make sure they're 50 ohm, right? 75 ohm, that's for video. 50 is for wireless. Okay, so here's what happens. Picture that the green line, that's the signal from your microphone. You've got a good, strong signal. You've got 30 dB of carrier to noise ratio, and your noise floor is at minus 92. Okay, that's good. Not a problem. But what I want to do is put a pad, and I want to turn that signal down from going into your radio. Now, when I turn it down 6 dB, I still have that same 30 dB of carrier to noise ratio. The voltage is lower, but I don't really care about the voltage until it gets crazy low or crazy high. Just like anything that I would consider normal to happen, I don't even usually worry about it. So we've got the same thing, but now we lowered the signal and we lowered the noise, right? So now we still have that 30 dB of carrier to noise ratio. If you remember from all the rest of the videos we've done, that's what makes your wireless mic work. That needs to be bigger than 20. So all we're doing is shifting the whole thing down. But it drops the noise floor from minus 92 to 98. And when it does that, the noise floor part of this does matter, because that's how your radio receiver sees its sensitivity. So when you drop the noise floor by 6 dB, you improve the sensitivity of the receiver by 6 dB. Carrier to noise stays the same, but you now have a better receiver, right? Because it sees less noise. SYNAD is signal to noise and distortion. And so we've improved that, and that's just going to make your receiver work better. This is another reason why we don't use amplified antennas. They go the other way. So they shift it up 6 or 10 dB, raise your noise floor. That makes your receiver 6 dB worse. It raises your voltage, but we don't really care about the voltage so much. What we care about principally is that carrier to noise ratio. So if I'd have shown you with an amplifier, I just would have shifted the whole thing up by however much gains in the amplifier. So we want to do it this way when you can. Now you have to make sure that you've got a strong enough signal, but you almost always will. Unless you're trying to catch your mic from 300 feet away or something. If you're on a stage, I don't worry about this much. So dropping those pads in line is going to improve your receiver. The next thing we want to do is try to reduce the transmit power of your in-ears or your microphones, either one of them. Turning them down reduces intermodulation. So let me show you how this works. My intermod, for every 1 dB that you increase the signal power, you increase the intermod by 3 dB. And this runs away in a hurry. So we're starting to picture this, okay? So that signal is now, there's 2 microphones, because one doesn't create intermod, but when you put 2 together, it creates intermod. And I've set that, so these are just signals from a signal generator. I've set that to be, I've got my carrier to noise ratio there. And what I'm going to do is as we go through these, I'm gonna increase the power 1 dB at a time. And 1 dB, look, okay, 1 dB, you can see the signal's not going up very much, but look how fast the intermod is coming up with it, right? It's getting crazy. Now we're adding extra harmonics to the intermod. And by the time I've raised this signal 20 dB, look at all the garbage I added that simply wasn't there when I was turned down. Now, I had enough carrier to noise ratio that I would have been good. So turning up my power made things worse. I had plenty. So walk test your system. Just, put it on. If you've got the system that switches power, most in-ear monitors do, most newer wireless microphones do. You go in on somewhere on the software page and just switch it. And you want to turn this down to the lowest power that works. You don't need high power on your in-ear monitors unless you're trying to get somebody on the other side of a football field. If they're on a stage and you're 100 feet away, low power works just great. And you'll reduce all this extra garbage. So with this extra garbage, of course, we're putting, well, let's see. You see it side by side. Okay, there's the same signal on low power and turned up 20 dB, and you can see all the extra garbage that we added, and you can see the noise floor is getting higher. And that's just with 2 mics. Now imagine if this was 8 microphones, this would have added thousands of those little harmonic lines, tens of thousands. So this runs away with you very quickly. This intermod. So low power, as low as you can work. Turn it on, turn it down, take your mic as far out as it's ever going to be, and make sure that it still works. But it probably will. So you turn it down as low as you can. Right now, you could turn it down too low, I guess. But most new wireless mics, most of the new digital wireless mics are working on 1 milliwatt and 10 milliwatt transmit power, right? They used to work on 30 and 50, and now they're working just fine on 1. So you'd be surprised. I know this seems backwards. Everything else you've done, it seems like, the more extra power you have in reserve, the better. But it's not in reserve anymore. You're actually using it. When you're using it, you're creating this intermod. So this is something we want to watch. Okay, here's one that probably isn't obvious, but if you want to pick up a little extra quality in your signal, again, we're reducing intermod. You have to think about, if you're using in-ear monitors and a combiner, which channels go into what inputs. So let's consider I got 8 in-ear transmitters into an 8-channel combiner. Could be an RF venue combiner, could be another brand. You could have 16 channels, you could have 4 channels, whatever it is. I'm just going to show you 8. Okay, so most people would put, channel 1 with the lowest frequency, and then they just run it up as they go, because it's easy to, it makes sense to figure out what's where. Channel 8's my highest frequency, channel 1's my lowest frequency, or the other way around, or whatever you've done. It just seems logical. That's the way we do things. But when you're working with a combiner, an 8-channel combiner, what you're really working with is 4 2-channel combiners. Now, they're not passive. It's not this simple, but this is the concept. You're really working with a bunch of 2 channels, right? And so what's happening here is the separation between those 2 channels dictates how much intermod and the power. But we're not going to change the power. We're just talking about the channel assignments. So the separation between those 2 frequencies is a factor in how much intermod it generates. The closer they are together, the more intermod it generates. The farther they are apart, the less intermod. So while this all makes sense and it's logical and it's easy to see, this works better. So instead of, and I should say, these numbers that I put up are fictitious. I just did 1, 2, 3, 4, 5, 6, 7, 8 because it's real easy to see. You'll never, well, you might see these frequencies, but I'm not saying tune to these frequencies. That's not the point. The point is the distance between them. And I'm just trying to make it easy to illustrate. So don't go out tuning your stuff. The frequencies that you tune to have to be appropriate for where you are. It might be these, it might be some other ones. That's not the point. We could have started at 520 or 550 or 58, didn't matter. I just wanted to make it simple. So we're just seeing 1, 2, 3, 4, 5, 6, 7, 8. Okay. If I plug in the 5th highest frequency into channel 2, now my separation between the 2 is much greater, right? By the way, I do like to keep at least 1 megahertz apart with in-ear transmitters. I think that's what I always try to shoot for, at least 1 megahertz apart. Anyway, so you can see if I have 501 and 505 together, I have much more separation, right? So we're just going to do this all the way down. So 502 is going to partner up with 506, and I'm going to maintain that 4 megahertz distance in between them instead of just the 1 megahertz I had when it was 503 and 504, right? So now look at the numbers. So in channel 1, if I've got 501, then I pick the fifth highest frequency, 505, and then 502 and 506, 503 and 507, 504 and 508, right? Is that sinking in? It's like all these numbers. Okay. So they're written down there. And so what you're trying to do is you're trying to keep each pair as far separated as you can over all these channels. Now, it's probably never going to work out this nice and smooth, but whatever you can do this on however many channels you can is just going to relieve some of that intermod, right? So the whole trick, everything we're trying to do here is to just keep one additional straw off the camel's back. Every straw we can pull off just makes our system that much better. Do you have to do these things? No. But being smart and doing them is going to make your system more reliable, because there's going to come that day, you know. So we want to do all these things. So just understand the concept. Don't put close channels together. Spread them out over whatever your frequencies are as best you can, like this, across the pairs, right? Now, there is a downside to this. And that's that we would like to keep our cluster. I mean, we could put them, if we had gone backwards, I should go back. What if we started with every one of these, 5 megahertz apart? Well, that would create lower intermod too. And if all you were doing was in-ear monitors, that wouldn't be such a bad idea. But I'm guessing most people are doing in-ear monitors are also doing wireless microphones at the same time. And so those two things have to live together, right? So let's go back to that. So when we would like to keep things clustered, right? So in that particular example, I have an 8 megahertz cluster, right? I'm going from 501 to 508. That's an 8 megahertz cluster. That's pretty good. If I'd have used 2 megahertz between, if I went, 501, 503, 505, I can't do the math beyond that because I can't use my fingers to count. Then I would have had a 20 megahertz cluster, and I'd have had 20 megahertz of intermod. See, if you look at the upper left-hand corner of that, where the blue arrows are, you can see my cluster is that width, and I'm also adding that width on top and below that cluster for my primary sources of intermod. So what I'm trying to do is not let that intermod mix with the intermod from the microphones. They're nice and clustered too. The bottom example, you can see both of those I've spread out, and now the intermods blend over the top of each other. So it's a double-edged sword. and it might be that one thing works better for you than the other. But if you can balance both of these things out, so try to keep your clusters small, like under 10 megahertz for your mics and your ears. Now I should say that's an in-ear monitor thing. You don't have to worry about your antenna distro. That they're not connected that way. That one doesn't matter. But on your ears, the way you assign channels is going to matter. So keep these two things in mind when you're hooking up your in-ear monitor system. This one we've talked about before, and I think a lot of people, right. Use software, yeah. I'll get around to it someday. Someday's coming very soon. All the wireless microphone manufacturers offer a free program. Unfortunately, we no longer offer this little scanner. If you've got one, good. If you don't, the newer wireless microphones in the last couple of years all network, and they'll plug right into these programs, and you just tell it how many mics you have. You can use the receiver itself to scan. Does a pretty good job. It's better done with an external scanner, but external scanners are expensive since we no longer have this one. Anyway, without this, it's a crapshoot. I mean, you're just going to get lucky to pick your channels, and I get so many phone calls. My distro's not working. And it's like, well, yeah, it's working fine. What's wrong is your channel selection. And it's hard for people to understand. Again, this is all invisible. Everybody thinks, well, I don't have any interference because I can't see it. Well, it's not smoke. It's not going to be in the air for you to see. You have to measure it. And these programs are going to, they're going to take the available channels and the scan, and they're going to divide them up for the best possible situation for right now, for right where you are. So if you're using Shure mics or Audio-Technica mics or Sennheiser mics, and you can mix and match. If you're using some Shure and some Audio-Technica, you can do that. You have to enter a little more stuff. Like you go to the Shure one, all the Shure products are there. If you want to enter Audio-Technica products, you're going to have to hand type in a few. Likewise for the Sennheiser. So, but you can mix and match all this stuff. That's not a problem. So go look at these. There are tons of YouTube videos how to do it. I guess Wireless Workbench is the most ubiquitous one. Probably more people use it. There's hundreds of beginner YouTube videos for exactly how to do this. And yeah, you'll pull your hair out for the first 20 minutes while you figure it out, but it's really not very difficult. And this is going to make your system work so much better than using the auto scan functions. Just don't work very well. They're really handicapped. And in the old days, 5 years ago, they were fine, but they just don't do a very good job. These two, so much better job. There's two parts to making a wireless microphone work. RF Venue can help you with one of them. We're going to get the signal from your transmitter to your receiver and give you a nice clean signal. But once it gets there, you have to pick a good channel to put it on. And I can't help you over the phone with that. So get one of these programs. You'll be doing yourself an enormous favor. If you can find one of these scanners, great. If you've got newer radios, you can just plug them in and go with that and do a pretty good job for free. So if you've already got those wireless mics, you don't have to spend any money. You're just going to have to learn a computer program for 10, 20 minutes. But it's pretty easy to do. And if you're ordering new microphones, just on the fly, like I'm here and I need 8 new microphones. What blocks should I get? If you go to our blog on the bottom of our webpage, down at the bottom, you're going to find this block, and this is going to tell you how to pick frequency blocks for your area with respect to the best thing you could select to avoid as many TV channels as are in your area. So this is a real good up-to-date. There's other ways to do it. Actually, you can kind of do it using those programs, but those programs tend to be way behind. They might be 6 months behind in picking the TV channels. That stuff is pretty fluid, and those programs may not be real up-to-date. This program's probably up-to-date within 24 or 48 hours, where those other programs might be 6 months behind. So, if you're buying new mics, you're going to want to do this before you spend the money and find out you've painted yourself into a corner. So that's on our blog, on our webpage, down at the bottom. Use interference filters. This one's going to cost you the most money, but you want your system to work and you just don't want dropouts. This is a huge thing. So if you haven't seen this before, this is a sweep that I did in Las Vegas about 2 months ago. Where we're using wireless mics is above the green area here, but there's interference down on the bottom from video walls and LED lighting. There's interference on the top from T-Mobile 5G phones. And what our problem is the dark green. The dark green is additional noise that's added from intermod from T-Mobile mixing with your wireless mics or the video wall mixing with your wireless mics. You plug these bandpass filters in, and this is what you're going to get. We'll just give it a second. It's actually happened. It just takes a while for the screen to show it. So look at that. All the rest of that garbage went away. Now, if you've got to find channels, it's pretty tough to find them there, and it's pretty easy to find them there. So this is the biggest positive thing you can do to your system to increase its reliability, because every time there's somebody in your audience or your congregation and they have a T-Mobile 5G phone in their pocket, they are competing with you for space. Okay. And if you've got video stage lighting or you've got video walls, that kind of thing, that's competing with you for space. Now, you're probably not going to turn off all that stage lighting you just bought, but if you put the bandpass filters in, we can make your wireless mics think it went away. I should say this is for wireless mics. This won't help you with in-ears. This is for receivers. But it's real simple. All you got to do is pick one of the bandpass filters. So these are the ones that we sell. They're very simple. They don't need to be tuned. Most bandpass filters, you need a scanner and a oscilloscope to tune them. Ours just plug and play. So there's 4 different flavors available, and all you have to do is be able to tune your mics anywhere between the bottom and the top number that are on these. They don't have to match your microphones. Your microphones just have to be able to sit inside. So if we looked at the upper right hand, it says 470 to 530. If your mics went from 490 to 540, they would be fine. You wouldn't be able to tune above 530, but you'd still have all that space, and it would now be nice and clear. So you would be giving up a little bit of your tuning possibility, but you'd be so much easier to tune in a clean band pass between that. So again, these don't have to match your frequency. You just have to be able to fit inside them. A little bit or a lot, doesn't matter. Just fit inside. And then they just plug in. There's no power. There's no tuning. There's no buttons. There's no switches. I'm telling you guys, this is an amazing benefit. And frankly, I don't think your system's going to work 2 years from now without it. I mean, it depends where you are. Obviously, if you're in the middle of Times Square, you needed this last week or 6 months ago. And if you're on top of a mountain in Idaho, you might have 2 years. Everywhere in between's everywhere in between. It's going to depend. It depends how much stage lighting you got. It depends how much video walls. Depends how many people are in your audience with 5G phones. But this is a big one. You really need this. Okay, so the next thing I want to talk about is your squelch settings. So a lot of people don't quite understand. Your squelch setting is going to be set for your wireless microphone. When you take it out of the box, it's set expecting your little whip antenna, right? So what the squelch does, it says when the signal has become low enough, I'm going to assume there's no more speech, there's no more singing in that microphone. It's just the hiss and the noise from the silence, right? You turn your mic on and nobody's singing, nobody's talking, and it's picking up your air conditioner a little bit. So it says, if I set the volume low enough, I don't need to pay any attention to this. It's like a noise gate, right, for your wireless mics. Okay, but it's set assuming that little whip antenna that you've got. If you're only using one wireless microphone, use the whip antenna. It might be fine. Probably is, If you're using a system, though, you got more mics, you're going to need a distro. You'd like to have a directional antenna. There's a whole bunch of benefits. We've talked about the benefits of diversity antennas that RF Venue makes. We won't go into that now. But you have a stronger signal. So you have to adjust. Just like with your mixer, if you had a dynamic microphone, you had your mic trim set, and then you unplug that and you plug a higher gain condenser mic, it's going to go crazy. You're going to distort your board. It's no longer, the system gain is off. Nothing's broken. You just need to adjust it. So that's what you need to do with your squelch. So what you're going to want to do is turn your squelch up higher. So your squelch conceptually sets the distance that your antenna is going to search out, right? So look at this graphic. So let's say your wireless microphone, I should have put the receiver on the other side where it says high and low. So let's say that side's your receiver and your microphone is some distance away, well, from your antenna actually, is some distance away from your antenna. What is that? 50 feet, 100 feet, whatever it is, 300 feet, but most people it's like 30 or 40 or 50 or 80 feet. Okay. If you turn your squelch up so that it only goes as far as your microphone, as your transmitter, it's only finding the amount of noise between the antenna and your transmitter. If you leave it the way it came out of the box, it's searching much farther than your microphone. And there's more noise out there. There's more RF interference out there, and it's going to find it. There's no use in having your antenna search 300 or 600 feet if you're only going to be 50 feet away from your antenna. So take your transmitter to the farthest spot in your room that you ever expect to work from, adjust the squelch control till your microphone goes off, and then bring it back a little bit. And that way you'll pick up, you won't pick up extra noise. That extra noise is adding to your noise floor. So this is a big thing. The other thing I get all the time, people go, well, I just plugged in my new distro and all my receivers are going crazy. Yeah, they are. They're searching 600, 800, 1,000, 10,000 feet for a signal because you don't have your transmitters turned on. When you turn your transmitters on, it'll lock up and that noise will go away. But if somebody turns off their mic, it's gonna start searching for forever. You're gonna find all that noise, and it didn't gate off, so it's gonna come through your PA. You're gonna hear a bunch of noise. So adjust your squelches if you've never done that since you took your mics out of the box. Turn them up some. So I think with that, we've about run out of. Yep, I actually ran over a minute, but I've got a few minutes if you want to hang on. And we got any questions there, Mr. Adam?
We have been answering the questions on the question and answer, so I'll let this opportunity for any more to come in now. But I can call out some of the questions that the attendees asked before they showed up. So I picked a couple of those. Let's see what I could do here. Pull that up. All right. So,
well, Adam, I think we should just quickly mention the one about the inline filters. You need two of them for the diversity systems. Don, there was a question about that.
You need one for each antenna. Yeah, you need one for the A side and one for the B side.
Yep, I thought I got that on the question and answer, but good to get it again to reiterate. Yep. All right. What are the differences in positioning transmit and receive antennas?
The differences in positioning? Well, that's called polarization. So we've covered that before, but I'll tell you again. It basically means if you consider a whip antenna and a handheld wireless microphone, when they're both in the same plane, the transfer is maximum efficiency. As they twist, you lose that efficiency. And by the time you get all the way this way, you will have lost more than 20 dB of signal. So your receiving antenna is now seeing less than 1% of what your transmitter is sending. Where when they're lined up, it's seeing 100%. You know, I mean, there's a loss for distance, but it's as efficient as it can be, and its efficiency can fall to less than 1% when it's twisted. The diversity fin antennas, all the diversity antennas take care of that. It's automatically compensated for. It can't happen with those. But when you use two separate antennas, you can have that problem. Even if you put one up and one sideways, because they're not seeing the same signal. So they both can go dead at the same time. Most of the time they'll switch, but you still will have circumstances where you'll get dropouts. Where with the diversity antennas that we make, that's not possible. You will never lose the signal.
Awesome. I think that answers it. I only bring it up because I think it's a very commonly asked question. So I wanted to make sure that.
Yeah, that's on our blog too, or it's in some of the webinars too. If you want to go back, if you haven't seen any of these, if this is your first one, we've got, I don't know what, 15 or 20 of these little webinars online on our YouTube channel, on our RF venue page. Yep. You can see all these things. So if you have some of those questions, you can find them there.
Here's a new question we've been getting a lot of, Don, so I think this is good. What is the diversity architectural performance compared to the diversity fin?
It has a little less gain. So if you're actually going to use one of these to their distance, I mean, normally a diversity fin antenna is going to be good for it depends where you are, but normally I'm going to consider that about 300 feet or so, which is way beyond what anybody needs. So at a given venue, if you could get 300 feet, let's say, out of your diversity fin, you're probably going to get 250 feet out of a diversity architectural, maybe 200, but in a room, that would be a darn big room. So if it's a classroom or a church that holds, 400, 600, 800 people, it's going to be fine.
Great.
Just a little less gain. Otherwise, it it behaves just like the diversity fin.
Great. This is a good one that may dispel some myths out there. I'm ready to hear this. How many digital mic systems can realistically be used in one venue?
In one venue?
Yes.
Oh, tens of thousands. I mean, I don't know what the real number is. So the only I'd have to do the math. Digital wireless microphones need to be tuned at least 600 megahertz apart. So if you had a venue that had zero RF interference, which will never happen, had zero TV channels, then you could put them 600 megahertz apart across 470 to 608, whatever that is, 160 megahertz of bandwidth. It's a lot. It'd be a really big choir. Yeah, there's really no limit. You know,
Gotcha. So
comfortably hundreds and hundreds of them.
good to know. So here's a good one that we get often, and I think you can answer this pretty well. I assume this person is asking about in-ear monitors. We get loud pops, gunshots during performances. Could RF dropouts cause this? Or maybe it's mics, or maybe it's ears. Maybe you could wrap that into both for mics and ears.
Well, it could be both. I mean, if you're getting you know, I mean, if you're on stage and somebody flips on a motor, maybe your air conditioner comes on, and everything's just lined up right. I mean, there's a brief RF spike, and so it really doesn't have anything to do with the antennas of the distros. What it has to do is what's creating the spike, and how does your receiver handle it. So better receivers handle it better than less expensive receivers, but that's just you know, that's something that could happen. The bandpass filters will help with that to block things that are out of band. I'll tell you what we get where that happens commonly. If you're working venues where there are people with security radios and they get anywhere near your antennas, when they key that on, it'll make a pop. Even though they're not in your frequency, those radios are so powerful, you know, that they're hundreds of times more powerful than your wireless mics. And so even the tiniest noise is hundreds of times louder than the noise that would be in your wireless mic. So security radios can cause that to happen. If you're working big shows and that kind of thing, or any place where, you know, where they've got guys walking around with walkie-talkies, don't let them get close to your antennas. Distance helps, but they've got so much power. So it's always power and distance. So that it could, like I said, it could be somebody switching something on. Really, anytime you flip a switch that turns on something that draws more than 2 amperes at 120 volts, it creates a pop.
Well, there you go. He just said he has stage comms. But he did, as a follow-up on that, to how would you monitor, I assume, with using RF spectrum analyzation to see what's happening?
Yeah, I mean, you have to use a scanner and see where that pop's coming from, and you got to be looking. I mean, it's probably really short. It's probably happening for less than half a second. So you got to be seeing it when it happens to see what it is, and then you try to figure out what it is by the frequency that it is. That's a tough problem to solve. I mean, you know, like I said, if it's the motor in your air conditioner switching on and off, and your air conditioner is going on and off every 10 minutes, you're going to get a lot of them, and you know, it's hard to trace down. But that's what it is. It's something external, probably. Now, in in-ears, I should add extra. In-ear belt packs don't work as robustly as wireless microphones work. Because with a wireless mic, you've got 2 receivers, and with almost all the in-ears, you've only got 1. And they're all analog. So analog radios are very touchy to signal quality. Analog radios, the quality changes with distance. If you have an analog wireless microphone at 10 feet, and then you back up to 50 feet, your quality is not as good at 50 feet as it was at 10 feet. With digital, it doesn't matter. But you're actually, and it's it's an infinitesimally small amount, but I can measure it all day long. So your belt packs are just for in-ear monitors are touchy. That's why you have to use a circular polarized antenna. Otherwise, regular whips or paddles just are so unpredictable about that. You're going to get birdies and pops and distortion and noise because almost all the in-ear monitors are analog.
Very good, Don. Well, with that, I think we've got enough questions here for you. And if any of you have further questions, feel free to email me directly, adam@rfnu.com. We're happy to help out. We will be posting this recording to our webinar page. So definitely check that. You can find that in our resources tab on our website, and look forward to the next webinar. Thanks for your time, Don. This was very informative as always, and we're looking forward to seeing you again on the next.
All right. Thanks, guys, for spending the time with us. We appreciate it.